Good, very early afternoon. Welcome to today's thesis discussion, as if we have one of these, dissertation defense, as if we have one of these every day. It is my pleasure to introduce Andrew Kleinschmidt. Andrew is finishing his 6th year as a PhD student in my group in chemical engineering. Andrew graduated from Stanford in chemical engineering in 2014. Actually, we have the distinction of being lab mates because when he joined the group the BAU group at Stanford in 2012 as a rising junior, I was an outgoing postdoc, and then we didn't know each other in that 1 month of overlap that we had because I was getting ready to start here 10 years ago. But then after graduating from Stanford, Alex worked in industry at Centrillion for 2 years doing like DNA microarray stuff. And then when he decided to go to grad school, he had lots of options and turned down an offer at the #1 chemical engineering school to come here to study chemical engineering. And I am eternally grateful for that. And I think you'll see that that decision was wise, or that turned out good for everybody, let's say. Last year, there was a really big scare in Andrew's life. So Andrew had a significant skiing accident and a traumatic brain injury, which left him in a coma for 5 days with a thereabouts, and in the hospital for a month, and in outpatient rehab for several months after that. And we were more than concerned. We were thinking that there was a chance. Well, one, Andrew was lucky to escape with his life, first of all. But then 2 months after his coma, he was on Jeopardy. And was in one of the 5 episodes that was taped with LeVar Burton, Geordie LaForge, and to just burnish his engineering credentials, and then returned to his research on fire, and really has done so much work in the last year, not just to catch up, but going above and beyond catching up. And when Andrew first joined the lab, I asked him, what do you want to do that's going to end up in a textbook? Like that's the goal here. We want to come up with something, do something together that's going to have a deep and lasting impact on physical organic chemistry, especially applied to organic electronic materials. And I think Andrew has done that. So I'm really excited to have Andrew share his work with you now. And take the floor, Andrew. Let's give him a warm welcome.
Thank you so much, everyone. Thank you, Darren, for those kind words, and happy Friday the 13th to everyone. It'll be a little bit of fun. So I'm going to talk to you today about the fundamental rigidity of pi-conjugated polymers. And so what are pi-conjugated polymers? So here is sort of the prototypical pi-conjugated polymer. You've got a polymer, or a plastic, a polymer chain, wherever it's a repeating chemical motif over and over again. And the thing that makes conjugated polymers conjugated is you have alternating double and single bonds in your polymer chain. And that can give rise to electronic behavior, and that could allow a lot of things potentially for the future. So you could have stretchable electronics, so transistors, all the things that make up your cell phone, all the things that make up your computer. Those could be stretchable. Those could be bendable. Those could be skin adhesive. Additionally, a new area of research in the Lipomi group is hard OPV, or hard organic electronics. So we're trying to take these organic electronic films and we're trying to make them hard. So here's an example of inorganic solar cells on top of a car. You could have a solar car, for example. That's not great. These things are easy to crack. These are easy to cause mechanical insult to. However, if you could just make the car paint into a solar cell, that would be much, much more optimal. And you can do that potentially with conjugated polymers. So what makes these things electronically active? So I talked about the fact that they have these alternating double and single bonds. So if you've taken college-level organic chemistry, you probably remember benzene. So this has similarly a sequence of alternating double and single bonds again and again. Benzene doesn't actually look like this, though, with the alternating double and single bonds. It actually looks more like this. So those pi bonds, so there are sigma and pi bonds. The pi bonds, the electrons that are above and below the plane of the benzene ring, they're delocalized. They're smeared across the entirety of the benzene ring. So instead of having a series of double and single bonds, you have a bunch of basically 1.5 bonds. And this can happen in conjugated polymers. This can happen in conjugated materials. When the conjugated rings are coplanar with each other, the electrons can delocalize not only within one ring, but they can delocalize between a lot of adjacent rings when they're coplanar with each other. That's energetically favorable. Electrons repulse each other a lot of times. So it's energetically favorable for them to get as far away from each other as possible. So things like to delocalize, and that results in fundamentally a rigid polymer chain. So as an example of this, so here's a standard polymer, polyethylene. It's just a series of single bonds over and over and over again to create a chain. So this is a standard plastic that it's probably in your water bottles. It's anything plastic. This is a strong candidate to be one of them. So I like to think of these things as a necklace. So polyethylene would be just a very simple necklace wherever it's flexible, it's bendable, it lies flat on your skin no matter, if your collarbone is broken, the polyethylene will still lie flat against it. In comparison, conjugated polymers, they're these series of ring structures, and the rings themselves are very brittle. So I think of this as a series of a necklace wherever it's a chunky necklace. There's a series of rings all next to each other. So they like to lie flat. What they ideally would do, the energetically favorable form of them is to lie flat, but there can be torsions nearby, there can be twists, and that creates chunky necklace. With conjugated polymers, the big thing that we need to know about the fundamental rigidity, how chunky is our necklace here, it gives rise to the electronic properties of the conjugated polymer. So when these conjugated rings are coplanar with each other, the electrons can delocalize. That's energetically favorable. That's what it also wants to do, and that's electronically good. That dictates its electronic properties. Additionally, just like with the necklace, it dictates the mechanical properties as well. Will this be brittle? Will this be hard? Will this be tough? Will this be stretchable? It dictates all of those properties, how much the rings desperately want to lie coplanar with each other. So this is a fundamental property of conjugated polymer systems. So people have tried to look at this experimentally. So people have done different diffraction studies, X-ray diffraction, small angle neutron scattering, but this generally requires a synchrotron, so it's very low throughput, it's very hard to do, and also you get sort of, you're looking for the fundamental rigidity of the system. However, you're getting sort of everything combined together, not necessarily the fundamental rigidity, but just how the rigidity interacts with steric hindrance, all these other things. So what people have done for a long time, because it's much higher throughput, is a quantum mechanical, a computational method of looking at this. So the thing that is standard for conjugated polymers is right now is a torsional scan. So you start out with your two conjugated rings coplanar with each other. And then you twist one of the rings more and more, and you use a quantum mechanical method to see how the energy changes. As you start blocking off this delocalization between your conjugated rings, you measure the energy again and again through your quantum method. Now, this was the standard for a long time with conjugated materials. However, you want to take this quantum mechanical data and put it into something where you can see how all of these rings are interacting and how they're all oriented with each other. So again, think of the ring. There are going to be twists. There are going to be, not everything's going to lie perfectly flat. We want to see how much that's happening in an actual conjugated polymer film. So the method for doing this a lot of times is using a force field. So a simplified description of the interactions between atoms in a material. So what we'll really be adjusting here is the dihedrals. So these simple four-body terms, and that defines the torsion. That defines how twisted these conjugated rings are between each other. And that's going to substantially change the energy based on allowing or blocking this electronic delocalization. But these non-bonded interactions, they're taking place between almost every atom in the system. And these non-bonded interactions are also going to be really dominant at some times in our torsional scan. So that's something that we're going to want to address in the future, or that my project is going to be addressing quite heavily. So a better descriptor of this dihedral torsion, we've got two conjugated rings, two simple conjugated rings from polyethylene. They start out coplanar, and you can see that they twist slowly. That's a dihedral twist. That's what we're describing with the dihedral twist. And whenever we go and we take our torsional scan, wherever we say, okay, this is this is the rigidity of the polymer, we end up a lot of times with things that are very, very twisted. So we're not getting an accurate descriptor of this one fundamental thing that describes the properties of conjugated polymers, that describes its electronic properties, that describes its electronic properties. We're getting these highly twisted materials, and we know that that is not fundamentally accurate. And so the way that I came into all of this is I started out experimentally. So I worked, and one of the first projects that I worked on was this huge polymer chain shown up here. And there was a tiny difference in the polymer chain. So in blue, where there's AR, we had either a single fused conjugate or fused thiophene ring, or a double thienothiophenane. And we saw big differences in the actual properties of the film with just that small change to the backbone structure. So whenever our polymer had the two fused rings, thienothiophenane, BCP-TT, the mobility, the electronic properties remained constant no matter how much stretchable block we added. In comparison, with only one fused ring, it plummeted quite quickly after adding the stretchable block. So just small changes to the backbone structure and small changes to the fundamental rigidity of the system result in large changes to the property of a conjugated polymer. And the thing is, right now, with conjugated polymer research, as these things, we're trying to make these things industrializable. We're trying to get better than just the P3HG that I showed you at the start. And there are a lot of different candidates for that, and they're very, very different chemically. So you get some huge fused ring structures, you get double ring structures. They're very, very different. So we need to be able to say, okay, what are the fundamental properties of these things, and be able to predict their behavior, because synthesizing them, it takes a very long time. So if you're synthesizing a new conjugated polymer, a lot of times that will take a postdoctoral organic chemist a year to synthesize a new one. And that's just not fast enough. We want to be able to go faster. We want to be able to look at this all computationally. So the big problem in general we want to go through more and more of these conjugated polymers. We want to be able to use computational techniques to look at the function of conjugated polymers. Chemistry itself is just not rapid enough because it takes too long to make new materials. Computational techniques right now can be used theoretically to model the fundamental properties of pi conjugated polymers, but these particular properties of conjugated polymers, their fundamental rigidity, is not well looked at because these things are oftentimes heavily designed for protein simulations. And so they're amazing at protein simulations, but they don't necessarily take into account these specifics of just conjugated polymer simulations. So we need to create a system to look at these things, these special type of conjugated polymers uniquely. And some interactions in conjugated polymers are completely ignored because these things are looked at for different types of materials and a sort of a generic force field is used. And we want to create something that, sorry.
Yeah, if you don't mind.
Yeah.
What do you mean by many interactions? What would be an example of? You mean like a sulfur fluorine interaction? What kind of what do you mean?
By types of interactions, I'm about to actually go into this in the next slide, so I can just go into this. So first of all, the fundamental rigidity between two conjugated rings in a system, that's just not accurately defined. That's including both the delocalization interaction and additionally all the non-bonded interactions, and those are oftentimes competing with each other. We also, improper torsion is something that is not looked at in general in conjugated polymers. So I'll talk about this a lot more in the future, but I talked a lot about dihedral torsion. So that is going to block off electronic delocalization within a conjugated polymer. They can also undergo improper torsion. They can sort of swing like a door hinge. So it's unclear, it's really unstudied right now, whether that improper torsion is blocking off extra electronic delocalization, or also it could be causing the pi systems to overlap with each other. It could be actually energetically beneficial. And so we need to look into this. More and more of our conjugated materials are highly twisted, and they're still having these really good electronic properties. So this could be an avenue to look into for these effects. And additionally, in a conjugated polymer, whenever you have a lot of these conjugated rings adjacent, they interact over a long distance. We know this experimentally. We know this from things like Raman spectroscopy. We want to calculate the coupling between these torsions in a conjugated polymer. All right, so there are three goals to each. There are three goals for each project that I'm talking about here. We want things to be more accurate. A fancy model is good, but if it doesn't accurately portray the morphology of a film, then it is not useful. Additionally, we want universality. So just like I was talking about before, these conjugated polymers, these conjugated materials, they're more and more heterogeneous. So they're more and more structurally different. We want our system to be able to apply to any of these conjugated polymers. And finally, intelligibility. So we want experimentalists to be able to look at the information we gained and be able to incorporate easily our information into their own experiments. All right, so let's get into project number one. So at the start of this, I was looking at it and it was, okay, the rigidity in these pi conjugated polymers is not defined accurately. So we want to look at the fundamental rigidity in the system. We want to look at this fundamental property, but with the torsional scan, we're getting back the energy related to delocalization. So the dihedrals in a conjugated polymer are the only thing accounting for electronic delocalization, but we're also in that incorporating non-bonded energy. So effectively, we're double counting our non-bonded energy and not properly counting or undercounting our delocalization energy. So we're going to get a very, very twisted polymer, and then all of the properties that we would predict from that are going to be inaccurate. So our goal is to develop a new and better method in order to look at this. And we want to develop and test it. Pretty simple for project number 1. So here's an example of the problems that I was talking about. So for the fundamental rigidity, for this fundamental property of conjugated polymer systems, 0 and 180 degrees, when these things are perfectly coplanar with each other, that's when you're going to get the most electronic delocalization. That should be, from a rigidity standpoint, the lowest energy state. But in almost all of these conjugated polymers, you get an energetic bump near 0 and 180 degrees. That's because whenever these things are perfectly coplanar with each other, you get steric effects. These things start clashing into each other, and that is not energetically favorable. So that we're double counting those effects, and because that acts contrary to the fundamental delocalization energy, we're undercounting this fundamental delocalization energy.
But you say it says MP2, so the quantum is getting it wrong also.
Yeah.
Okay.
So so just all of the simulations are carried out in MP2.
Oh, I see them. That you can just hardly see the
Sorry.
but they are there.
Yeah.
Really great.
All right. So the method that I did to try to isolate this delocalization energy, so I started out with simple torsional scan. So just 2 rings and a conjugated polymer. I twisted them over and over, used a quantum mechanical method. For me, MP2, over and over again to see how the energy would change. I then repeated this hydrogenating one of the conjugated rings. So the hydrogens would block off these pi electrons from being able to delocalize between each other. And so by eliminating this, this delocalization energy, we could come up with an approximation for just the non-bonded energy. Yeah.
So the MP2 is okay for the delocalization, it does capture the delocalization.
Yeah.
So can you go back?
Yeah.
Yeah, I think I agree with you. Where is the MP2? Can we see it?
It's actually, the MP2, it is very light and white here, but it's effectively the same as the OPLS.
But I thought the OPLS is wrong, right?
So they fit the OPLS to the MP2, so I actually don't know why they wrote that down as 2 separate things. But yeah, the OPLS, the dihedral torsion, is parameterized based on their MP2 measurements.
So this is an extension of OPLS that captures the conjugation?
Yes. So I think the OPLS is just a fit to the OPLS parameter set for dihedral torsion for their MP2 energies. So whether it's fit with that.
As you said that this force field does not capture conjugation.
It captures the conjugation, so it captures the electronic delocalization, but it's also capturing all these other things with it. So the steric effects, the fact that the things that are pushing away from linearity, it's also taking into account. So it's double counting that, and because this is the only thing encouraging linearity between the conjugated, it is destabilizing the fundamental rigidity of the conjugated polymer.
That effect is identical with MP2.
So,
if it's wrong, then why is it with MP2?
So I would think of this as it's a difference between so the overall energy of the system. So the overall things that will be shown by this, that is shown by MP2. So if we were just taking a quantum mechanical descriptor of the overall energy of the system, that would be great. For molecular dynamics simulations, we've already got the non-bonded effects, all those non-bondeds. Those are included through the Leonard-Jones parameters or whatever. So we want to just include the one extra thing, that electron delocalization that is not accounted for. And this is accounting for everything here. All those things that are already accounted for, that's also in the MP2. So the MP2 is showing extra, it is double counting something and undercounting the actual fundamentals of the system. Yeah, so then when we put that into molecular dynamics models, we get extremely twisted structures. So a lot of the because we have nothing pushing towards copolarity.
So Andrew, when you say OPLS here, this is not actually the total energy of twist. This is just the dihedral energy.
Yes.
Yes.
Yes. So yeah, this is just the dihedral. Yeah. Okay, sorry. All right, so we're going through and we're trying to fit this dihedral and just the OPLS, the dihedral energy, just to the delocalization energy of the system. So here we've got, we start with the torsional scan, so just the same thing as before, where we get all the energy back. We then hydrogenate the conjugated, We then hydrogenate one of the conjugated rings to block off electronic delocalization. So we use that as an approximation for the non-bonded energy. For the fact that we're adding one of these non-physical hydrogens, we additionally do a correction where we have a method, just a methyl group with a non-physical hydrogen to account for any extra energy that might cause. We can correct for the non-bonded energy, get an approximation of the non-bonded energy. We can then subtract that off from the torsional scan to get an approximation of just the energy related to electronic delocalization. All right, so on the left here, again, we have just the torsional scan. We're getting just the torsional scan, and then the new approach is these extra parts to it. So we're just doing a correction to the torsional scan. We're getting more accurate energy. So I'm going to go through 3 polymers here. So there's P3HT. So this is sort of referred to as the fruit fly of conjugated polymers. So this is what every, this has been an extensively studied polymer over a large number of years. And so there's a lot of literature to compare our results to here. Also P2B7, that's a newer type of conjugated polymer, but one that's become increasingly popular. It's higher performance than P3HT. Additionally, it has 2 different types of conjugated ring next to each other. And one of those conjugated rings is asymmetric. So depending on which side that fluorine is pointed to, you're going to get very different steric effects. So a lot of times people in molecular dynamics simulations have treated these as completely different torsions, even though chemically the delocalization is the same between them. And finally, there's PNDIT. So this is from a popular class of polymers that's required for a lot of solar cells, for a lot of LEDs. So the big problem here is that these are highly, highly twisted a lot of times. And that seems to be because of the steric effects, because there are steric clashes when these things are coplanar with each other. So we want to see whenever there's really, really high steric effects happening, can we accurately depict just the delocalization energy, because right now things are coming back highly twisted. Also, we have 2 different types of polymers here. So the 2 polymers on the left largely transport charge in an absence of electrons, and the one on the right largely transports electrons. So we're really trying to achieve our universality here. All right, so what we end up finding, so the torsional scan method is shown in red here, and our new method for just the delocalization energy is shown in blue. So in general, the blue, our new method, shows the delocalization energy being higher. So things where our fundamental energy of the system was being undercounted before because we had these competing non-bonded steric effects and delocalization effects. Additionally, there would be problems in almost all of the polymers near planarity. We would get spikes in energy that don't represent the fundamental delocalization energy of the system. So for something like PB7 with a fluorine pointed in, we get around 130 degrees, fairly twisted polymer is the minimum energy. And this is the only force in our system that should be driving coplanarity between the conjugated rings. And then it increases again towards 108 degrees. And PNDIT, this polymer we said was very sterically hindered. The old method shown in red, that is fairly modern art. It is the minimum, the energy is minimized around 40 degrees, and there's really nothing pushing it towards planarity. Things just, all these steric effects dominate the whole system. whenever we try to check our accuracy here. So we randomize just 2 conjugated rings and see how accurately our force field, our OPLS-derived terms describe this system with our new method versus the old method. And particularly, so if we're comparing 2 dimer systems, dihedral with a dihedral 1, a second one with dihedral 2, whenever those are very different, we get the most accurate description of our polymer system. And the accuracy improves across all polymers, and particularly polymers with really high steric effects. Whenever we get rid of these non-bonded interactions, when we just look at the fundamentals and include that in our system, then we are getting the best improvement in our conjugated materials. We can also interpret this more easily. So in red was the old method, so we might compare either 0 or 180 degrees to 90 degrees to check the total torsional barrier, how easy it is to twist these things. Additionally, you might just compare the maximum energy versus the minimum energy. Depending on which one of these you do, that can make with the old version, with the red version, these things are very variable. They're not consistent except for with a fluorine out PDB7, but in general these are not consistent. The 2 different conformations of PDB7, depending on which way the fluorine is pointed, they have different energies, and PNDIT is undecipherable effectively. Depending on which version of this you choose, you get very different energies. In comparison with our new method, shown in blue here, we get a slow increase in rigidity of the conjugated polymer. So you can start to incorporate this into experimental research. So you can say, okay, I'm fluorinating this polymer, or I'm chlorinating this polymer, and I'm getting X kcal per mole difference in torsional barrier. I'm getting X kcal per mole more rigid of a conjugated polymer. And by varying that property, you can see what the effects on the electronic and mechanical properties are. Additionally, we put this into a full-scale simulation of a conjugated polymer. So, and across all the conjugated polymers, on bottom is shown which torsional angles are more common in our new method, and which one in red are shown which ones are common using the old method. Across all these polymers, more planar conformations are more common, particularly whenever the steric effects are really, really high. Whenever those were really high in the torsional scan, then we were getting very twisted conformations, and now we're getting substantially more planar conformations.
The x-axis label says it's 45 degrees. Is that just in this label?
I'm sorry. So I can collapse everything down to be between 0 and 90 degrees versus...
So it peaks at 45 degrees. That's not planar.
I'm sorry. It does peak at 45 degrees because you do still have the steric effects for a lot of these things. So for like P3HT, but it just shifts it 10 degrees lower for P3HT, and it shows substantially more at the lower, at the more coplanar effects. So it is still twisted, but it's not in like PNDIT, wherever almost everything was at like 70 degrees.
Thank you.
Yeah.
And so this is for the full potential, like not just looking at it.
Yeah.
So
Yeah.
does this have impropers then also, or no impropers left?
No impropers yet. That is project number 2.
Okay,
Yeah.
no, that's good. So there's no impropers.
There's no impropers here. Yeah, so everything is, there's no impropers. And then whenever we use this to approximate the conjugation length, these are things that we can look at through Raman spectroscopy. We know that these things have been undercounted before in the past. And with our new method, we get longer conjugation lengths. We're seeing more experimentally accurate conjugation lengths as well. So overall, what this project number 1 showed, we got a more accurate molecular dynamics description of our conjugated materials. And it was able to work on all of them, even these ones that before it would have been really hard to simulate these accurately, PNDIT. We were able to get much more accuracy there. And experimentalists, based on the plot that I showed, can understand the fundamental rigidity, how the fundamental rigidity is changed based on the data that is generated here. All right, so that was a good advance. So the next thing was talking about this improper torsion. For almost all studies, experimental or computational, of conjugated polymers, improper torsion isn't really well characterized. So I'll go more into what improper torsion is, but in general, it's not a twist. Instead, it's more like a door hinge movement. And so we wanted to look at how this improper torsion is interfering with electronic delocalization. Again, it's breaking coplanarity, so it could be blocking electronic delocalization. However, it could also be causing these pi systems to overlap. And so our new work is we're going to come up with a method to look at improper torsion. So we're going to do similar to Torsional Scan for our conjugated materials, and we're also going to couple together improper and dihedral torsion. As this delocalization is being affected, this should affect both improper and dihedral torsion. So we want to couple them together. And based on our past work, we're going to isolate just the delocalization energy that was very effective before, and we're going to see in a second that sterics are a big problem for conjugated polymers with improper torsion. Okay, so we talked about the two different types of torsion. Dihedral torsion is shown up top, and you can think of it as you're taking a screwdriver to something and the threads are stripped on the screw. So you're just rotating again and again, just twisting. Improper is more like a door hinge. So with dihedral, the center of gravity wasn't really moving. Improper, you're getting a movement in the center of gravity. These things are getting closer together, and they would completely collide if you had 180 degrees of improper torsion. Whenever we ran simple simulations on each of these polymers from before, we're using the same polymers as in the last study, we found that there was some degree of improper torsion, no matter how you use angular parameterizations, for example. No matter what, we were getting some degree of improper torsion. And if you're undergoing some sort of a non-equilibrium process, so if you're melt casting these things, that's very popular. If you've got a polymer film under strain, you're going to get even more of this improper torsion, very likely. So this is sort of represents a minimum, and it's always prevalent even then. And whenever it is, but to try to parameterize this, try to understand the fundamentals of improper torsion, as it increases, the energy just skyrockets in general. And so the reason behind this is likely because of the increased steric clashes between our conjugated polymers, particularly near planarity. So we're getting, because of these non-bonded interactions, we're getting huge energies for improper torsion. And additionally, this can be a problem because our improper torsion is going to cause a miscalculation of our dihedral torsion as well. So, so in blue and red are showed the conventional method of calculating a dihedral. And so for P3HT, for example, if you include both sulfurs as the ends of your dihedral, then it might decrease. If you included one of the carbons instead, it might increase, but you'll get something wrong. So what we did was we developed a method using collective variables to describe the system. So we input the energy of this into a collective variable system. We effectively hijacked a metadynamics method in order to put in these coupled torsions, and we were able to correctly calculate the dihedral no matter the improper.
The impropers, are the impropers you're talking about the ones on either side of that rotatable bond?
Yes. Okay. Yeah. So, and then I've got a term to include both of those together. But yeah. All right. So whenever we correct for the non-bonded energy, whenever we just look at the delocalization energy, we get a moderate amount of energy. So improper torsion causes moderate amount of energy that might be seen fairly commonly, particularly if it's combined with some sort of dihedral torsion to minimize non-bonded effects, or in general, this might avoid non-bonded effects. And for donor-acceptor polymers, high degrees of improper torsion are energetically favorable according to electronic delocalization. So like at 30 degrees, shown in red down here, it actually starts becoming favorable as these pi systems likely begin to overlap. We're getting some degree of favorability to this torsion as opposed to just monotonically being unfavorable. So it's a new, different type of torsion. And for highly twisted polymers, highly twisted things like P and DIT, this might be something that's allowing still good charge transport to happen, even though it's highly twisted and you would normally have electronic delocalization highly blocked off. In general, the way that this affects dihedral torsion, so showing the torsional barrier here, the difference between 0 degrees and 90 degrees of dihedral torsion in the polymer, it monotonically decreases. So that suggests that as more and more of this electronic delocalization is blocked off, there is less electronic delocalization to lose by having this dihedral torsion, or the pi systems are overlapping no matter what, and so it doesn't matter this dihedral torsion. Additionally, whenever we compare it to simply improper and dihedral torsion, our improper torsion is always stronger, so it does seem to be a stronger blocking of this electronic delocalization in general, but even then it's not so energetically unfavorable that you're not going to see it. And for PNDIT, once you start getting up to high degrees of improper torsion, it actually becomes more favorable. Whenever we included this into a molecular dynamic system, into a full model of our system, we got increased accuracy across all four polymers again. And we were concerned that this might be because of the removal of simply delocalization energy, and we saw a smaller but still substantial improvement in accuracy, even when we were comparing just dihedral torsion to an inclusion of dihedral torsion, and our dihedral torsion was corrected for non-bonded effects. All right, so what we saw in project number 2. We saw increased accuracy whenever we include the effects of improper torsion on our full conjugated polymer model. Universality, so again, we used those 3 very different conjugated polymers, and it worked more accurately across all 3 polymers. And finally, intelligibility. We were able to understand that there's a difference between dihedral and improper torsion. They are cooperative in some way. And for donor and acceptor polymers, high improper torsion might actually become energetically favorable from a delocalization standpoint. All right, so now we're moving on to project number 3. So we know experimentally that conjugated rings interact over long distances. The conjugation length of a polymer, how long a polymer charges can delocalize along, has been long understood as a fundamental feature of conjugated polymers. However, long-range interactions between these different torsions and conjugated polymers is poorly understood right now. So we want to develop a method to couple these torsions together and to understand how these torsions might be affecting each other. So the new work that we're doing, so now we're performing a torsional scan again, but we're performing it on every combination of these 2 torsions in a trimer system. Before we were just using dimers, just 2 conjugated rings. Now we're expanding to trimers. And we're coupling these torsions together as well.
Can I ask a question?
Yeah.
So when you say long distances then, then I'm thinking polymer really long, but you're talking about going from 2 to 3. Is there like,
Yeah.
what's your sort of thinking of
Yeah, so the thought was that this was sort of a first proof of concept. This was the first time that this had been introduced. And so, okay, we're going to go from 2 to just 3. Okay. And then, like, theoretically, there's nothing blocking this off from being used on longer range systems. It's just a lot more computational time. Yeah. So. And so the past work we're using, again, we're going to just try to look at the delocalization energy here. And we're going to use the coupling of torsions that we used in project number 2. We coupled together the improper and the dihedral torsion using a collective variable model. We're going to use that same collective variable model to couple these long-range torsions together. All right, so we're going to use just one polymer in this study. and it's DPP2FTT. So it's got these conjugated rings, and so more for the nomenclature, I'm going to refer to them from left to right as conjugated rings 1, conjugated ring 2, conjugated ring 3, and in general, I would just call this DPP furan TT. And this is the polymer that I was using before in my experimental studies that showed a big difference from whenever this ring was changed from TT, from polyethylene to just thiophene. So we know that there's something happening with just a small change in the conjugated polymer backbone. Additionally, these have very different electron affinities as conjugated rings. So DPP is a really strong acceptor. It really wants to take more electron density towards it. Thiophene is a really strong donor. So it really wants to get rid of electron density. And furan is a pi-rich. So the electron densities are just being delocalized between the furan, and it's supposed to not be strongly interacting. So in the past, the interaction between the DPP and the TT would not have been included in a model of our conjugated polymer. However, we would expect that these things, the donor and the acceptor, would be really strongly interacting. So we want to start including this. So if we just look at the two-ring systems like before, thiophene, the TT, and furan, those are fairly normally interacting around the same level of dihedral barrier as P3HT. In comparison, for our DPP and furan, this has by far the highest torsional barrier of all the polymers that we've tested so far. So thiophene and furan, those are both donor conjugated rings. In comparison, DPP furan is a donor-acceptor, a donor and an acceptor. So we would predict, based on this, that the DPP and the TT would be really strongly interacting. And what we find is that is true. So if we're looking at just the torsion between the conjugated ring 1 and conjugated ring 2, and we just add always coplanar a conjugated ring number 3. So here we add in the thiophene. On the bottom left, we add in the DPP unit, and on the right, we just add in another furan. So we see substantial changes to our torsional barrier, to our fundamental rigidity of the system, as we just add in, not twisting or anything, we just add in a third ring. So we get an increase from about 8 kcal per mole to about 10 to 11 kcal per mole whenever we just add in a thiophene, we just add in a TT unit. So we get a much more rigid polymer whenever we include this interaction between the DPP and the thiophene. Additionally, for the two donors, for TT and furan, whenever we add in a DPP unit, the torsional barrier increases from under 4 kcal per mole to over 6 kcal per mole. So just this interaction between the TT unit and the DPP unit changes the overall energy related to torsion, the fundamental rigidity, by over 50%. So that is a very significant interaction between these two. Whenever we try to just look at the interaction between the 1 and the 3 rings, so now we've got, we're changing around this torsion for the 3 conjugated ring. So as we go from blue to red, we're twisting that third ring more and more. Whenever we don't correct for non-bonded energy in general, we have a torsional barrier additional energy of interaction of about 2.5 kcal per mole whenever we add in a thiophene unit, and about the same whenever we add in a DPP unit. But in general, we find that whenever we do correct for our non-bonded energies, when we do correct for to just try to get the delocalization energy, we get more accurate simulations across all trimer systems. So whenever we actually include this, we find that the interactions are a little bit stronger between DPP and thiophene. in general. And additionally, what we find whenever we extract this non-bonded energy is that before we've always had energetic peaks, energetic maxima around 90 degrees in our conjugated polymers. However, with these pi bridges, they're meant to just shuttle along this electron delocalization in a lot of ways. It actually doesn't matter the conformation of that central, of that 2 conjugated ring. It wants to be coplanar with that furan ring no matter what conformation that central ring is in. So we get, instead of an energetic maxima at 90, we get an energetic maxima at 60 degrees whenever all of these things are not coplanar with each other, whenever we have all of these things twisted with each other. So that's an interesting effect that hadn't been seen before, and we're going to further explore. But I say the central tenet that we've learned from this study is that torsion begets torsion. So as you start undergoing torsion in your polymer chain, it becomes easier and easier as there's torsion for more torsion to accumulate in the same area. And that can have really big effects on the mechanical properties of your conjugated polymer film. These things are often highly brittle, and you're going from basically double bond strength or aromatic strength to single bond strength. So it's going to be easier and easier to undergo plastic deformation to rupture this polymer chain. So overall, we found that we got more accurate modeling. We were able to,
Why is rupture an issue here? Because it sounds like what you're saying is basically if everything's coplanar, possibly, that it's maximally conjugated, and as soon as you start breaking that, all the other ones don't care quite as much as, But that means that it would rotate more readily, but rupture sounds like bond breaking.
Yeah, so what I'm saying is that whenever this torsion is in effect, when this electronic delocalization is less in effect, you're getting less double bond character in these bonds. So it becomes easier to undergo that bond rupturing to pull those rings apart whenever you have less electron density over them. Yeah. So we're getting a more accurate description of our fundamental torsion in the system whenever we ignore our non-bonded effects too. We did this only with one polymer, DPP2FTT, but there's no reason that this shouldn't be possible on any other polymer. And we are able to understand these fundamental relationships to see that torsion begets more torsion. As these things are going to be under strain, the torsion is going to start accumulate, and that will have profound implications for the mechanical properties of the system. So overall, we are able to look at the fundamental forces of conjugated polymer systems. We are able to look at the fundamental rigidity of our conjugated polymer systems. We are able to make simulations more accurate by accounting for these non-bonded effects properly and able to look at just the delocalization energy. And this is helpful not just for conjugated polymers, but for any sort of system that has multiple conjugated rings. So liquid crystal structures, things like that, non-natural amino acids with long conjugation in them. This is possible to all of that. We are also able to use our method. We were able to account for that non-bonded energy, and we were able to get a description for the first time of this improper torsion and how it might be affecting electronic delocalization in the system. And we are additionally able to expand this using the things that we learned in the first few projects to include correlated torsions in the system. All right, and here are my publications over the past 6 years. I'd like to thank all of my co-authors for this, and I'd like to move into acknowledgments. So I'd really like to thank the Lipomi Lab, the Lipomi Group. That's a lot of you guys here today for all of the help and support they've given me. This is a newer picture, but everyone that's been in the Lipomi Group has really, really helped me and just been so kind and so welcoming. Also the Pascal Group, the Atlas Group has been really nice, really helpful. We need a group picture there. Yeah, COVID. I'd really like to thank my two PIs. So Darren has been extremely supportive. He is the reason I came to UCSD in the first place, and I was able.
Wait, I thought I was.
Todd came in year 3, was incredible, and like before that, it was, I was sort of scrabbling in the dark, and he came in and he was like, "Oh yeah, that's my research got really supercharged whenever Todd entered the picture, and just both of these incredible PIs have meant so much to me and given me so much latitude with my work to pursue the things that I find interesting, even rigidity of conjugated polymers." Robert is the grad student that is taking over computation in the conjugated polymers research, and I'm really excited for him, and I hope he has as much fun with it as I did. And Alex has been my editor, my senior editor. So he has gone through all of my papers, and he's, I think, really come to a great understanding of these fundamental properties of conjugated polymer systems. And it's been really great to watch him help me and make any of my sentences make sense. And I'd like to thank everyone who has supported me so much over the past 5 years. It's been, I've gone through a fair bit in the past year and a half. And I know that I wouldn't be where I am today. I generally studiously try to avoid looking up statistics of, like what percentage of people get a traumatic brain injury and then, hopefully get a PhD afterwards. I know that I couldn't be here without all the support of everyone and all of the kindness that I've received in the past really 30 years of my life. And you've all been so great and so helpful, and I hope this paints you a little bit proud today. And I'd really like to thank all of my therapists. A lot of them are shown on the left. Again, this is not a super standard route out from a brain injury, and I know that I would not have been able to accomplish everything that I was able to accomplish without all of their tireless effort and tireless help. And also organizations like ARCS, which were really supportive to me. They gave me an extra year of funding, and Suzanne Dixon was in contact with my dad all the time, always wanted to know what was happening. And just really great and really supportive. And my family for always being there for me, especially whenever things were tough and complicated, and just the best family you could ask for. Just flying out at a moment's notice, just suddenly living in San Diego whenever their son had problems, and just the level of support that I've received has been incredible, and I couldn't have done any of this without all of your help. So thank you.